In this lesson, we will discuss linear Diophantine equations. In the introduction video for this course, we discussed several ancient Greeks that contributed to early number theory. Linear Diophantine equations are named after one of these Greek mathematicians, Diophantus of Alexandria, who around 250 AD studied equations in two or more unknowns with integer solutions. Let's start with some definitions. An integral linear combination of integers a and b is an expression of the form ax plus by, where x and y are integers. So we've already seen integral linear combinations a few times. In particular, we looked at the fact that if a number divides a and b, then it'll divide any linear combination of a and b. And we saw that this had applications to the division algorithm and the Euclidean algorithm for finding GCDs. So the question that Diophantus studied and other mathematicians have studied are, suppose you're given two integers a and b. What integers can I write as a linear combination of a and b? So in other words, suppose I had an integer c. Is it possible to find an integer linear combination of a and b so that ax plus by equals c? So we'll answer the question, what values of c can be written as an integer linear combination of given integers a and b? A linear equation of this form is called a linear Diophantine equation. Linear equation of the form ax plus by equals c, where a, b, c are integers, is called a linear Diophantine equation. A solution to this expression is a pair x comma y of integers that satisfy the equation. So when we study linear Diophantine equations, we're only interested in solutions that are integers. For example, consider the equation 2x plus 6y equals 3. Can you find a solution xy that satisfies this equation? No, there are no solutions. Why? Well, look at the left-hand side. 2x plus 6y, that's the sum of two even numbers. So an even plus an even number can never equal an odd number. So an even plus an even number can never equal an odd number. So this linear Diophantine equation has no solutions. Well, what if I change the number 3 to an even number? So 2x plus 6y. It turns out that this equation has a solution if and only if n is even. So we'll see why this equation has a solution when n is even. Theorem. The linear Diophantine equation ax plus by equals c has a solution if and only if the greatest common divisor of a and b divides c. First, we'll prove the forward implication. Suppose ax plus by equals c is solvable. Since d, which I want to use to stand for the greatest common divisor of a and b, since d is a divisor of a and b, d will divide any linear combination of a and b. In particular, d divides ax plus by. And therefore, since ax plus by equals c, d divides c. Now we're going to prove the reverse implication. So in this part of the proof, we're going to assume that the greatest common divisor of a and b divides c. But first, we're actually going to show that I can write the greatest common divisor as a linear combination of a and b. Without loss of generality, we're going to assume that a and b are positive. We can assume that a and b are positive because x and y are integers And so if A and B weren't positive or negative, for example, we could just absorb the negative sign into x and y, and we'd still have a solution to our Diophantine equation. So in our proof, we're going to assume that A and B are positive. Now let's consider the set that contains all positive integral linear combinations of A and B. I'm going to consider the set of all positive integral linear combinations of A and B. Well, this set is not empty. Why? Well, actually, I can write A as a linear combination of A and B. A, which I can write as A times 1 plus B times 0. So I've written A as a linear combination of A and B, and I assume that A is positive. So since A is in this set, so this set is not empty. So we have a non-empty set of positive integers. By the well-ordering principle, this set has a least element, which I'm going to call D. By the well-ordering principle, this set has a least element. And I'm going to call this element D. The reason why I'm using D is because we'll see in a minute that this smallest element is actually the greatest common divisor of A and B. So D is a positive integral linear combination of A and B, so I can write D equals A times some integer, I'm going to call it x0, plus B times some integer y0. What I'm going to show now is that D divides A. I'll show that D divides A, and then we can conclude that D also divides B, so D is a common divisor of A and B. Then I'll show that D is the greatest common divisor. By the division algorithm, A equals a quotient times D plus a remainder, where this remainder must be greater than or equal to 0 and less than D. But I can rewrite R as A minus QD, and let's substitute in for D. So D, recall, is A times x0 plus B times y0. This actually is a linear combination of A and B. So if I distribute a minus Q, I get A minus a q x0 minus b q y0, and actually can write this as a linear combination of a by factoring out an a from the first two terms. This equals a times the quantity 1 minus qx0 plus b times negative q y0. So we see that R is a linear combination of A and B. If R is positive, then we would get a contradiction because we assume D was the smallest positive linear combination of A and B, and R is smaller than D. So if R is positive, then this would contradict the fact that D is the smallest positive linear combination of A and B. So R can't be positive. Therefore, R must equal 0. And A actually equals Q times D. Therefore, D divides A. There was nothing special about the letter A as opposed to the letter B, so by a completely similar argument, D also divides B. So we can conclude that D is a common divisor of A and B. So let's recap so far. So we're trying to show that if the greatest common divisor of A and B divides a number C, then AX plus BY equals C has a solution. What I'm going to show, what we're showing in this part of the proof, is that I can write D as integer linear combination of A and B. And then we're going to show that D actually equals the greatest common divisor. Then we'll show that if C is a multiple of D, then AX plus BY equals C has a solution as well. So next we show that D is the greatest common divisor of A and B. I've shown that D is a common divisor of A and B, but now let's suppose we have another divisor of A and B. So suppose some integer K divides A and K divides B. So suppose we have another common divisor of A and B. Then A equals Km and b equals kn for some integers m and n, then d, which remember equals a times x0 plus b times y0, replacing a with km, we see this equals km times x0, and when substituting for b, we get plus kn times y0, and if I factor out a k, this expression becomes k times mx0 plus n y0, and we see that k divides d. If k divides d, then k can't be bigger than d. So therefore, d must be the greatest common divisor, because any other divisor of a and b has to divide d. Therefore, d is the greatest common divisor of a and b. So we've shown that the greatest common divisor of a and b is actually the smallest positive integer linear combination of a and b. So we're going to now suppose that d divides c. So d divides some integer c. To finish this part of the proof, we need to show that ax plus by equals c has a solution. Since d divides c, I can write c as d times some integer, let's call it L, then c, which equals dl, equals, and I'm going to replace d with ax0 plus by0 times L. If I distribute an L, this equals a times lx0 plus b times L y0. Therefore, the integer pair lx0 ly0 is a solution to the linear Diophantine equation ax plus by equals c. So we've just shown that if d divides c, there is a solution to the linear Diophantine equation ax plus by equals c. Let's look back at the theorem that we just proved. So a linear Diophantine equation, ax plus by equals c, has a solution exactly when the greatest common divisor of a and b divides c. Here's a useful corollary to this theorem. Integers a and b are relatively prime if and only if ax plus by equals 1 has a solution. Why is this statement true? Well, by definition, if a and b are relatively prime, then the greatest common divisor of a and b equals 1. And we've shown that the linear Diophantine equation, ax plus by equals 1, would have a solution, because 1 is the greatest common divisor of a and b. Now let's look at some examples. Consider the equation 4x plus 12y equals 18. Does this equation have a solution? Well, let's look at the greatest common divisor of 4 and 12. 4 divides both 4 and 12, and it is the greatest common divisor, but 4 does not divide 18. So this equation has no integer solution. How about another example? Is the equation 33x plus 57y equals 6 solvable? Let's investigate. First, we need to find the greatest common divisor of 33 and 57. So, by the Euclidean algorithm, I will divide 33 into 57. 33 goes into 57 one time, with a remainder of 24. Now I'm going to divide 33 by 24. The 24 goes into 33 one time, with a remainder of 9. Now I'm going to divide 24 by 9. 9 goes into 24 two times, so 24 equals 2 times 9, plus a remainder of 6. When I divide 6 into 9, I get 9 equals 1 times 6, plus a remainder of 3. And then 6 equals 2 times the remainder 3 plus 0. So the last non-zero remainder is 3. So by the Euclidean algorithm, we see that the greatest common divisor of 33 and 57 equals 3. Since 3 divides 6, 33x plus 57y equals 6 is solvable. That means we can find integers x and y that will satisfy this equation. Well, let's find a solution to this linear Diophantine equation. The way we're going to find the solution xy is we're going to use the work we did with the Euclidean algorithm to rewrite each remainder as a linear combination of 33 and 57. So I'm going to rewrite each remainder as a linear combination of A and B. Okay. So let's start with the remainder of 3, the next to last equation from above. So we had 9 equals 1 times 6 plus 3. So I can write 3 as 9 minus 1 times 6 from the next to last equation. But from the middle equation, with remainder 6, I can rewrite 6 as 24 minus 2 times 9. So I'm going to replace 6 with 24 minus 2 times 9. So I'm using this equation right here to replace 6 with 24 minus 2 times 9. So let me collect like terms. I have a factor of minus 1 times minus 2 times 9. So that gives me a total of plus 2 times 9. And I have another 9 outside. So I'll have a total of 3 times 9 minus, when I distribute the minus 1 times 24. Okay, so I've written the last non-zero remainder 3 as 3 times 9 minus 1 times 24. Well, now I'm going to replace the number 9 using this equation. We see that 9 can be rewritten as 33 minus 1 times 24. So I'm going to continue this process. We see that this expression will equal 3 times 33 minus 1 times 24 when I replace the 9. And I still have minus 1 times 24. So I'm going to expand this a bit, and I get 3 times 33. I have a total of minus, when I multiply this together, I have minus 3 times 24, and I have a minus 1 times 24. That's going to give me a total of minus 4 times 24. So I've written 3 as a linear combination of 33 and 24. The last step, I need to replace 24 using the first equation, using the fact that 57 equals 1 times 33 plus 24. Therefore, 24, I can rewrite 24 as 57 minus 1 times 33. So this equals 3 times 33 minus 4, and I'm going to replace 24 with 57 minus 1 times 33. So I've actually written 3 as a linear combination of 33 and 57, but let's rewrite this. So I have 3 times 33. I have minus 4 times minus 1, which is 4. So 4 times 33. So I'll have a total of 7 times 33. And then when I distribute a minus 4 times 57, I'll get minus 4 times 57. So what I've just shown is that I can write 3 as 3 equals 7 times 33 minus 4 times 57. But we wanted to find a solution, an integer linear combination of 33 and 57 that equals 6. Well, if I just multiply both sides of this equation by 2, I'll get two times 3 is 6. And if I distribute a 2, that'll equal 14 times 33 minus 8 times 57. So the point 14 comma negative 8 is the solution. In the last example, we found one solution to a particular Diophantine equation. It turns out if there's one solution, then there's an infinite number of solutions. So we saw that the point 14 comma negative 8 is a solution, is a, say, a particular solution to the linear Diophantine equation 33x plus 57y equals 6. You can verify this, that if you multiply 33 times 14 plus 57 times negative 8, you do get 6. Okay, so we found a particular solution, but it turns out that we can write an infinite number of solutions based off of this particular solution. So we're going to find what we call the general solution. So I'm going to show you what the general solution is first, and I'll show you how to get it. So the general solution is the point 14 plus 19t comma negative 8 minus 11t, where t is any integer. So this general solution actually describes all the possible integer solutions to this linear equation. The particular solution that we found would occur by plugging in 0 for t. But if you plug in any other value for t, you get another solution to this equation. Let's verify this. Let's show that this is a solution. So what if I plug in 14 plus 19t for x? I'll get 33 times 14 plus 19t. And then plug in negative 8 minus 11t for y. We have to verify that this equals 6. Well, when I distribute a 33, I get 33 times 14 plus 33 times 19, which is 627t. Then when I distribute a 57, I get 57 times negative 8 minus 57 times 11, which is 627t. And we see that the positive 627t and the negative 627t cancel, and I'm just left with 33 times 14 plus 57 times negative 8, which we know equals 6. So we see that 14 plus 19t, comma, negative 8 minus 11t is a solution for any integer t. So now I'm going to prove a theorem that shows us how to find this general solution if we know a particular solution. So suppose we have one particular solution. So we know the coordinates x0, y0 of the solution. So if x0, y0 is a solution to the linear Diophantine equation, ax plus by equals c, then the general solution xy is the general solution where x equals x0, the x coordinate of our particular solution, plus b divided by the greatest common divisor of a and b, which I'm going to call d, times any integer t. Okay, so where x equals x0 plus b over d times t, y equals y0, the y coordinate of our particular solution, minus a over d times the integer t. Okay, so d is the greatest common divisor of a and b, and t is any integer. Okay, so using this formula, you can see I use this formula to find the general solution to the previous example. So let's see the proof of this theorem. Suppose ax0 plus by0 equals c. So in other words, suppose that x0, y0 is a solution. Okay, so let's plug in this general solution. So then ax plus by, which equals a times x0 plus b over d times some integer t, plus b times y0 minus a over d times t. Again, d stands for greatest common divisor. If I distribute, I get a times x0 plus a b over d times t, plus b y0 minus a b over d times t. And we see that these two terms involving t cancel, and I'm just left with a times x0 plus b times y0, which we assumed x0 and y0 was a solution, so this equals c. So I've just verified that this ordered pair xy is a solution to ax plus by equals c for any integer t. Now let's look back at the previous example. I demonstrated that 14 plus 19t, comma, negative 8 minus 11t was the general solution to this linear equation. But now I'm going to show you how I got this using the theorem we just proved. So we see that 14, -8 is our particular solution. We saw that D, the greatest common divisor of 33 and 57, is 3. Therefore, the general solution has x coordinate 14 plus b over d, so 57 over 3 times t, which reduces to 14 plus 19t, and the y coordinate for the general solution is y equals -8 minus a over d, so it's 33 over 3t, which reduces to -8 minus 11t. So that's how I got the general solution, 14 plus 19t minus 8 minus 11t, where t is any integer. Just as a final note for linear Diophantine equations, if there's one solution to a Diophantine equation, then there's actually an infinite number of them. All of these points with integer coordinates, if they're plotted in the real plane, will all lie on the same line. So the solutions to the equation ax plus by equals c are the points with integer coordinates sometimes called lattice points. Any points in the plane that has all integer coordinates is called a lattice point. So these solutions are all lattice points lying on the graph of the line ax plus by equals c.